Okay, and today we are going to discuss a new section 4.5, which is called Basic Integration Formulas. So the idea is similar to the idea of the derivatives. So we know the definition of derivatives, but actually we don't use the definition frequently, rather we use some rules. And the same story happens here. So it's hard to use the definition of the integral, but instead of that, you can develop some rules, and using these rules, you can calculate many examples. But before going there, let's introduce some notation. So recall that integral from a to b, a function f of x dx, is called definite integral of f from a to b. This is one thing. And also we have our fundamental theorem of calculus that says that if you have such integral, then we can find it using the antiderivative evaluated point B minus point A. In other words, f of B minus f of A. And in some sense, because of this, we'll introduce one more definition, and it will be called indefinite integral, and it is the following. Of some function f. It has the meaning of the antiderivative, but for some reason it is more useful. So what I'm saying that, first of all, it looks like this, integral of f of x dx, where you don't specify upper and lower and upper limits, and it is equal to some antiderivative of your function f. Why should we do that? Again, basically the connection is the following, that if you want to calculate our definite integral, then we need to find antiderivative, and just to have the same notations in some sense, we introduce this indefinite integral. But also, you can now see that differentiation and integration are in some sense inverse to each other. So what I'm saying, that, say, consider differential of some antiderivative of x, then it is just, by the definition, it's the same as this integral. But we know that it is the same as f of x dx, because we know that f prime of x is exactly f of x. This is the definition of the antiderivative. So indeed, maybe better to write it in this way, that it is f prime, capital F prime of x times dx, but this is, by the definition of the antiderivative, is f of x dx. And so we got that d integral f of x dx, differential of the whole indefinite integral, is f of x dx. So in some sense, differentiation and integration are inverse to each other. And it turns out that the opposite is also true, because if you have derivative of some function, then antiderivative will be just f of x, maybe plus some constant. And thus, integral of differential of f of x is the same as integral of f prime of x dx for the differentiable functions. And it is the same as the process of finding antiderivative of f prime, and the antiderivative is f of x plus constant. And so what we get, that integral of df of x is equal to f of x plus constant. So in some sense, that's why integration is inverse operation to the differentiation. Yes, this is just notation. So now the process of finding antiderivative we will call integration. Capital F of x of some function f of x is called integration, and it is equivalent to finding the following indefinite integral. And so now we can rewrite our formulas that we discussed in section 4.1. If we have f of x as x to the power n, then the corresponding antiderivative was x to the power n plus 1 over n plus 1 plus some constant. And now I can say, using this notation, that the integral of this function xn gives me xn plus 1 over n plus 1 plus some constant. So it's nothing else but just writing this fact in different notation. The same story happens with the constant function. If our function is just constant function, then we discuss that the antiderivative, capital F of x, is x times k plus constant, and thus I can say that integral of k dx, which is the same as just antiderivative of k, is equal to k times x plus some constant. And we can combine these two formulas and see that integral of k x to the power n dx thus will be k integral xn dx, which is k xn plus 1 over n plus 1 plus constant. There is a general property which is called linearity of the integral. So integral is linear. That means if you have two functions that multiplied by some constants c1 and c2 times g of x, then the integral is in fact sum of two integrals, and you can put constant in front of each integral. So it is equal to this plus c2 times g of x dx. And it is not hard to see, because again, if you want to check that it's indeed true, we need just to differentiate. So recall that there is corresponding capital F of x corresponds to small f of x, so it's antiderivative of small f of x, and capital G of x is antiderivative of g of x. Then if we, so what is written here, that c1 f of x plus c2 g of x is antiderivative of function that is c1 times f of x plus c2 g of x. But I'm saying that this function, let's call it L of x, is in fact antiderivative for c1 f of x plus c2 g of x. That's what we need to prove, because the left-hand side in the box is just the antiderivative of this function c1 of f of x and c2 plus c2 g of x. And how to check it? We just need to differentiate. And indeed, if I differentiate this, then using that differentiation is linear, that means that the derivative over the sum is sum of the derivatives. I can write it like that. This we want to show. C2g, capital G of x prime. And again, using that constant can be put in front of the derivative. It's equal to this plus C2 G of x prime. But since capital F of x is antiderivative for f, I got indeed that it is small f of x plus C2, the same story with capital G of x. So indeed, I got the function which derivative gives me C1 times f of x plus C2 g of x. So it's my derivative for C1 f of x plus C2 g of x. And thus it is the same. So in other words, linearity of the derivative transforms in the linearity of the integral, which is this one. And the basic idea that some rules that you know for the derivatives transforms in some rules for the integrals. Let's consider the following generalized power rule. So we know that such rule exists for the derivative, and thus it should be something in integration that corresponds to that. So what is the generalized power rule? Let's do it for the example. So suppose we have function f of x, which is x squared plus 1 squared. Then using generalized power rule, the derivative of this function gives me, so I should differentiate second power, and that gives me this, and times derivative of the function which is inside. And so I get that it is 2 times x squared plus 1 times 2x. Or using the differential forms, so df, which is f prime of x times dx, is equal to 2 times x squared plus 1 times 2x dx. And again, as we discussed at the beginning, if I integrate both sides, so far it's just formally, so what I'll get? I'll get integral of the differential, which is the same as by the formula above to this one, 2 times x squared plus 1 times 2x times dx. But this is, as we discussed, just the function itself, maybe plus some constant. And what we got that integral of 2 times x squared plus 1 times 2x dx is equal to x squared plus 1 squared plus some constant. So in some sense, we are going backward. So we found some formula coming from the generalized power rule, and then we transform it to the rule for the indefinite integral. And let's try apply this idea to the following integral. Suppose we have integral, so it's another example, integral of 1/2 x squared plus 1 to the power minus 1/2 times 2x. So it is quite similar to the one that is in a blue box. And what we want to do, we want to find some function such that this integral is equal to something like integral of df for some f. And then using the fact that integration and differentiation are inverse to each other, we will get just f itself. But the question how to find this f. And the point is that if I consider function which is x squared plus 1 to the power 1/2, then indeed it will be differential of this function, because using the generalized power rule, what can I see? So first I differentiate power 1/2, so it gives me x squared plus 1 to the power minus 1/2, and then derivative of this, which is exactly the integrand that I have. Dx everywhere. So it's derivative times dx, derivatives times dx, if I consider differential. So indeed, I found function such that the integrand is differential of that function. And thus, this integral will be that function itself plus some constant. So these two examples are just generalized power rule in reverse. And let's recall what is generalized power rule. If I have some function u of x to the power n, then its derivative is equal to n times u to the power n minus 1 of x times derivative of that function. Or if I write it in differential form, d of un of x is equal to derivative that is written above un minus 1 of x times u prime of x times dx. And let's integrate it. So apply integral to the both sides. I'll get integral d of u to the power n of x is equal to integral n times u n minus 1 of x times u prime of x dx. But as we discussed, integral of differential is the same as the function itself plus some constant, u to the power n of x plus some constant. And on the right-hand side, I can notice that n is just a constant, and as we discussed, I can put it in front of the integral, while this term is actually du, right? Because what is du of x? It's exactly derivative of that function times dx. And thus I get that on the right-hand side, I have n integral u to the power n minus 1 of x du. I can express my integral of u in the following way. So I get that integral u to the power n minus 1 of x du thus will be u to the power n of x divided by n plus some constant divided by n, but this is again just some different constant, say c tilde. That's what is called general power formula. So integral, and let's consider u to the power n of x du is equal to u to the power n plus 1 of x divided by n plus 1 and plus some constant. And it works when n is not minus 1. And it's again actually true for any rational n except minus 1. Another form of this formula is this, that u n of x times u prime of x dx is equal to the same right-hand side. This form is slightly larger, but it shows how to find your function u. Let me show you that in our previous example. So we had integral 1/2 times x squared plus 1 to the power minus 1/2 times 2x dx. So if we compare the formula that is in the blue box and what we have in our example, we see that the candidate for u is function x squared plus 1. But also we should find something that corresponds to u prime. Let's see that. So u prime thus will be 2x. And so I can write my integral in the following form, that it is integral 1/2 u to the power minus 1/2 times 2x, which is u prime of x, times dx. So exactly the form that is in the blue box, except that I have 1/2, but it's just a constant that I can put again in front of the integral. And thus, by this formula, so I can write it as 1/2 times that integral, I will obtain u to the power which is minus 1/2 plus 1 divided by minus 1/2 plus 1. Plus some constant. But this is 1/2 u to the power 1/2 divided by 1/2 plus constant. So we see cancellation here, and thus we obtain the same result as we got before. But I need to make one more step, because now I have an answer in terms of u, while initially I have integral in terms of x. So now I need to substitute it back. So my u is x squared plus 1, and so I get that the final answer is x squared plus 1 to the power 1/2 plus some constant, which is indeed the same answer as we have seen before. Again, the idea is first you need to find u, then check that there is also u prime inside your integral, and then you can use this general power rule. The short form is the first one, but actually when you're trying to apply it, it's usually better to think about this formula in the second form. So let's do more examples. Example number 2. Let's integrate x squared square root of x cubed plus 1 dx. Or I can write it as integral x squared x cubed plus 1 to the power 1/2 dx. And again, we should find u to some power and derivative of that u. And here are two candidates. Either my u tilde, say, is x, and then I have here u tilde squared, but then I should find the derivative of this u, and the derivative of this u with respect to x gives me 1, while I have some function which doesn't look like 1. So probably this is not a good choice for function u. Thus, let's consider u, which is x cubed plus 1. Then the second term will look like u to the power 1/2. And let's see what happens with the derivative. Derivative of this function will be 3x squared plus 0, so just 3x squared. And it's almost like the first term, except that I don't have 3. But of course, I can multiply and divide by 3, and I'll get this integral. And now I indeed see that this is my u to the power 1/2, while this is u prime and dx. Or you can think that the whole, if you like, first form, then you can see that this is the same as d of u, which is 3x squared dx. So it's u prime, which is 3x squared times dx. So either that way or another, now we can use our general power rule. So if I can make one additional step, so it's u to the power 1/2 times du, if you like the first form again. But this is the same as u to the power, which is 3/2 over 3/2 plus constant. And if I simplify it, it will give me 2 over 9 u to the power 3/2 plus constant. But this is not the final answer, because my initial integral was in terms of x. So my final answer should be also in terms of x. So I need to substitute back. And so I got 2 over 9. Then I have u, which is x cubed plus 1, and to the power 3/2 plus constant. And this is my final answer. Okay, let's do more. Let's calculate the following integral: x dx over third root 1 minus x squared. Or again, I can rewrite it as x times 1 minus x squared to the power minus 1/3 dx. So here, again, there is natural choice for u, 1 minus x squared. But we need to check that there is also u prime in our integral, which is in this case will be minus 2x. And indeed we have x, and again 2 is just minus 2 is just a constant. So as I did before, I can multiply and divide by minus 2. And so I'll get minus 1/2 integral 1 minus x squared to the power minus 1/3 and minus 2x dx. So again, I multiplied it by minus 2 and divided by minus 2. But this is just u to the power minus 1/3, while this is u prime times dx, or just du. So I get minus 1/2 integral u to the power minus 1/3 du. And by general power rule, it gives me so minus 1/2 u to the power minus 1/3 plus 1, which is 2/3 divided by 2/3, and plus constant. And thus it is minus 3 over 4 u to the power 2/3 plus constant. And I need to substitute back. My u was 1 minus x squared, and thus the final answer is minus 3 over 4, 1 minus x squared to the power 2/3 plus constant. But unfortunately, general power formula doesn't always work. So consider the following example: integral dx over square root of 1 minus x squared. So I can write it as integral of 1 minus x squared to the power minus 1/2 times dx. And if we try to choose u as 1 minus x squared, then indeed we'll get here u to the power minus 1/2. But when we calculate the derivative of u, it will be minus 2x. But there is no minus 2x inside our integral. Or even just x, there is no, comparing to the previous example. So in this case, I cannot use my general power formula because it doesn't work here. That's why you should study other techniques, how to integrate. Unfortunately, in this course, we will not cover it, but there are integration by parts, more general substitution rule, and trigonometric substitution, and so on and so on. So general power formula is just one of them, but not the universal one, unfortunately. Okay, let's do next example. Integrate the following: x squared minus 1 squared dx. So if you try the natural choice for u, which is x squared minus 1, then we'll have the same problem as in a previous example, because u prime will be 2x, and again, there is no 2x inside our integral. And so we cannot use general power rule. But the point is that we still can integrate this function, but in a different way. Let's just expand second power. So I'll get x to the power 4 minus 2x squared plus 1 dx. So I got just polynomial, and we know how to integrate it. So I get x to the power 5 over 5 minus 2x cubed over 3 plus x and plus some constant. The next example illustrates that we can use general power formula in case of definite integral. So suppose we want to evaluate definite integral from minus square root of 6 to minus 1 x dx over square root of 10 minus x squared. There are two options. First one is the following. So let's use our general power rule. So I can write my integral as integral from minus square root of 6 to minus 1 x times 10 minus x squared to the power minus 1/2 dx. And so natural choice for u will be 10 minus x squared. Then u prime of x will be minus 2x. And du of x thus will be minus 2x dx. So indeed, I have here u to the power minus 1/2, and this is almost my u prime, except that I need to multiply by minus 2. So let's multiply by minus 2 and divide by minus 2, and I'll get minus 1/2 integral 10 minus x squared to the power minus 1/2 times minus 2x dx. And thus I will get indeed minus 1/2 integral. So this is my u to the power minus 1/2 minus 2x dx is du. And so indeed I can use general power rule. But the question is, what happened with the limits? So before I had minus square root of 6 to minus 1. And what should I write here? I cannot write here also minus square root of 6 and minus 1, because my u is not the same as x. So remember that what is integral from a to b f of x dx? This corresponds to the area under the curve f of x, where x runs from a to b, right? And now, after I choose u as some function of x, I'll obtain integral of some function of u du. And now I need to find the corresponding interval for u. Let's call it capital A and B. And how to find this interval? You can find it using the formula for u. So in our case, u is 10 minus x squared, right? And we know that x runs from minus square root of 6 to minus 1. And thus we can see that the left endpoint should correspond to, by this formula, to the left point for the u interval, which will be 10 minus square root of 6 squared, or 10 minus 6, which is 4. While the right endpoint, using the formula, should correspond to point B, which is 10 minus 1 squared, which is just 9. And so we get that the corresponding interval for u is from 4 to 9. That are my new limits of integration. And so I can come back to my integral. So I get minus 1/2 u to the power minus 1/2 du. U to the power minus 1/2 du. And the limits now are 4 and 9. And using general power rule for integral, I obtain that it is minus 1/2 u to the power minus 1/2 plus 1, which is 1/2, divided by 1/2, and I need to substitute from 4 to 9. And I see some cancellations, and thus I will get minus square root of u, substitution from 4 to 9. And that gives me minus square root of 9, which is 3, minus square root of 4, which is 2, or just minus 1. So this is first option, where you can use general power rule and change the limits and obtain the final answer. There is another way to solve this. So second option. So again, we have this integral from minus square root of 6 to minus 1 x 10 minus x squared to the power minus 1/2 dx. And let's now forget about the definite integral. Let's try to calculate the antiderivative for the function under the integral. So in other words, let's calculate indefinite integral. X 10 minus x squared to the power minus 1/2 dx. And repeating the same steps, so again, my u is 10 minus x squared, u prime is minus 2x, and so on. I will obtain that this integral is the same as minus 1/2 integral u to the power minus 1/2 du. Since it's indefinite integral, I have no problems with limits. And using general power rule, I obtain that it is minus square root of u plus some constant. And if I substitute back, I'll get that it is minus square root of 10 minus x squared plus some constant. So what I got? I got antiderivative for my function. So this is antiderivative. Let's call it capital F of x. But now I can use the fundamental theorem of calculus that says that integral from a to b f of x dx is equal to antiderivative substitution from a to b. So I found my antiderivative for the initial integral, and now I will use this fundamental theorem of calculus. So I get that integral from minus square root of 6 to minus 1, x 10 minus x squared to the power minus 1/2 dx is equal to minus square root of 10 minus x squared, substitution from minus square root of 6 to minus 1. Again, there is no constant because it's the same and it disappears. And so I got that it is minus square root of 10 minus minus 1 squared minus minus, so it's plus, square root of 10 minus minus square root of 6 squared. So I get 10 minus 1, which is 9, and square root of 9 is 3. 10 minus 6, which is 4, and square root of 4 is 2. And so I obtained the same result, of course. Minus square root of 3 plus 2, which is minus 1. So either you use first option, and then you need to think about the corresponding limits, how to transform them, or you use second option, and then you need first calculate antiderivative, and then substitute your limits. But both ways are, of course, correct.